In this video, we will be going over the phases and events of an action potential, as well as how to read an action potential diagram or graph. It's a pretty stereotypical diagram, so it's important that you guys know what happens where and what the mechanism behind each process are. So starting off, this is our action potential diagram. If you notice on the y-axis, we have voltage in millivolts, and the values range from -70, -55, 0 to +40 millivolts. And on the x-axis, we have the time in milliseconds, and it ranges from 1 millisecond, 3 milliseconds, to 5 milliseconds. And so starting off with the resting state phase, which is depicted right here, we're at the -70 mark along this flat line, and then also here along the -70 mark along with the flat line here. And so the resting state is where the neuron is at rest with a stable membrane potential. And so indeed it is stable since it's flat in the horizontal orientation here, and it's flat horizontally here. Inside of the neuron is negatively charged relative to the outside, maintained by sodium-potassium pump, 3 sodium out, 2 potassium in, and leak channels. Moving on, we have the threshold at -55 millivolts. And so the stimulus causes the membrane potential to become less negative. And here, indeed, we see the stimulus depicted by this arrow here causes the membrane potential to increase in value, becoming less negative. And once it crosses this threshold line, it's going to then continue depolarization. If the depolarization reaches the threshold level, approximately -55 millivolts, voltage-gated sodium channels will open. And so once we reach the threshold level, once again, the membrane will become less negative, and sodium channels open, and sodium rushes into the neuron. Moving on, we have the depolarization, which is right here. It follows along this flat line in the vertical orientation, and it's characterized by a rapid rise in membrane potential. And indeed, we can see that's also true. It goes very quickly up until it hits the +40 peak. Sodium ions rush into the neuron through voltage-gated sodium channels, making the inside more positive. And so, yes, once we hit the threshold, depolarization occurs, sodium channels open, and sodium rushes into the neuron. Next, we have the peak of the action potential, which is right here at the very top, corresponding to the +40 millivolt mark. The membrane potential reaches its maximum positive value. And indeed, we can also see that's true. It's the highest point in the graph. Voltage-gated sodium channels begin to close, and voltage-gated potassium channels open. And so this is depicted here, where we see sodium channels close, potassium channels open, and potassium rushes out of the neuron. Next, we have the repolarization, characterized by the other right side of this peak here. And so the arrow will go down like this. And it's the return of the membrane potential to a negative value. And indeed, it goes to a negative value and even becomes more negative. But we'll get to that in the next step. Potassium ions exit the neuron through voltage-gated potassium channels, restoring the negative membrane potential. And so, like I mentioned again, Once we hit the peak of the action potential, sodium channels close, potassium channels open, and potassium rushes out of the neuron. Next, we have hyperpolarization, depicted by this dip here. And it's when the membrane potential temporarily becomes more negative than the resting potential. And so the resting potential is at -70, but here we go below -70. So it becomes even more negative than it would be during its resting state. And during hyperpolarization, voltage-gated potassium channels remain open longer than needed, causing an overshoot, which is when it becomes more negative than -70 millivolts. So this here is the hyperpolarization stage, but this dip here can also be characterized as an overshoot. And so after the hyperpolarization occurs, we will be then returning back to the resting state right here. And so the resting state is when the membrane potential stabilizes back to resting level. Sodium-potassium pumps and leak channels restore the original ion distribution, bringing the membrane potential back to -70 millivolts. And as we can see, this is what happens right here. We go back to -70 millivolts. And so to recap everything, the action potential diagram is very simple. We have the -70 millivolt mark, which is where the neuron is at the resting state. If a stimulus is detected and it brings us over the threshold level at -55 millivolts, then depolarization will occur, characterized by the voltage-gated sodium channels opening and sodium rushing into the neuron. And then the membrane potential will become more positive until it hits the peak at +40 millivolts. The peak then is characterized by voltage-gated sodium channels closing, voltage-gated potassium channels opening, which allows potassium to exit the neuron. As the potassium exits the neuron, the membrane potential will start to become more negative again, characterized as repolarization, until it hits the -70 mark and then temporarily dips below the -70 mark in a stage known as hyperpolarization, where this is also considered as the overshoot. And then as the potassium channels close and the sodium potassium pump and leak channels bring the ion distribution back to normal, the resting state will ensue at -70 millivolts. I hope you guys enjoyed the video. Please let me know what you think in the comments below and be sure to like and subscribe.